Hey guys, so let's go through some of these sample diploma questions. I'm not going to go through the homework because all the answers were there. If you had trouble with anything in the homework, just shoot me an email and I can go through it, or I can talk with you via email, or we can Google Meet and figure that out. Okay. So these sample diploma questions. Cosmic radiation has a higher frequency than gamma radiation. So frequency is a hard thing to like visualize and picture, but wavelength is a lot easier, right? And remember that with V equals lambda F, if we have a higher frequency, we have a lower or smaller wavelength. So we're looking for something with a smaller wavelength, and wavelength is the distance from here to here. So the only one that has a smaller distance from crest to crest is going to be A, and A is the correct answer. Ultraviolet radiation with a frequency of that has a wavelength of that. So ultraviolet is part of the electromagnetic spectrum, so it travels at the speed of light. So we got to use C equals lambda F, and we are trying to find a wavelength. So we go C divided by F. So all we need to do is take the speed of light, which is 3 times 10 to the 8, and divide it by our frequency, which is 2.8 times 10 to the 17, and we get this as our answer. So our answer is going to be, how does it want the answer? A, B, and C, so 1.07 times 10 to the, what was it again? Negative 9. So it would be 1079. Okay. So we're going to talk about all the different types of electromagnetic radiation today. So you need to describe the range of the electromagnetic spectrum. You need to know about radio, micro, infrared, visible, ultraviolet, X-ray, and gamma. Those are the ones that you need to know, and those are the ones that are in your data booklet. We're going to talk about the source of these different things. So we talked about the wavelength, and we'll also talk about the energy today and their effect on living tissue. So we need to talk about that as well. And we also need to recognize that the Earth's atmosphere absorbs certain frequencies of EMR. So we're going to start with the smallest frequency, biggest wavelength, lowest energy. So this lesson is going to go from lowest energy to highest energy. So radio waves are the lowest energy, and because they have such a low energy, they are unable to penetrate metal objects, and that's why you need an external antenna for like FM and AM radio. You need an antenna on your car because the radio waves are so low energy they can't get inside of your car, so you need that external antenna. So when EMR enters the antenna, it causes electrons to vibrate in that antenna, and that vibration of electrons is a signal, and is decoded by the circuitry in your radio, which is really cool and amazing technology. So radio waves, because they're so low energy, they have almost no effect on living tissue and are safe to be around in all situations. Right now, you have radio waves traveling through you at all times. Right, that you can pick up an FM radio anywhere that you are, so that means that there's radio waves all around you, and they are nothing to worry about. Microwaves. So when we think of microwaves, we think of microwave ovens, and microwave ovens are just a specific use for that's in the microwave range. So microwave ovens use the specific frequency of 2,450 megahertz, so times 10 to the 6 hertz. The reason that microwaves use this frequency is because this is a frequency where water molecules will start to vibrate, right? Anything less or anything more than that won't get water molecules to vibrate, but this is the resonant frequency of water, and it causes it to start to vibrate. Kind of like if you lick your finger and circle it around a wine glass, it starts to hum. It's the same sort of idea with that resonant frequency. So when the water molecules vibrate, it starts to warm your food, right? They vibrate back and forth, they create friction, it warms your food, and that's what's happening with microwaves. So you wouldn't want to send microwaves out at 2,450 megahertz because we have a lot of water in us, and that would cause our water molecules to vibrate and would cook us. But even if someone sent out that signal, it wouldn't be enough energy to actually cook you. You'd have to like climb inside of a microwave oven to actually cook yourself. If you're further away from the microwave oven, even with the door open, like 2 meters away, it just wouldn't have enough energy to do anything. And there's a misconception about microwaves. People hear microwaves and they think, oh, it's going to cook you. But microwave is what Wi-Fi runs off of. So Wi-Fi in your house is a microwave signal. Cell phones run off of microwaves. And the great thing about microwaves is that they can penetrate rain, snow, smoke, which makes them great for radar or satellite or cell phones, right? This is why they run on this range, because they can travel through anything in the atmosphere. So that's what makes them really great. So people are concerned about electromagnetic radiation. They're concerned about microwaves. And here's a video that is absolutely ridiculous that I found on Instagram about people buying these EMF blockers. Cell phones run off of microwaves. So if you actually used one of these blockers, your cell phone wouldn't work. And if cell phones were actually dangerous, everyone would have cell phone cancer by now, because cell phones have been around since the early 80s, and there is no link with any dangerous health effects in microwaves. So microwaves are 100% fine to living tissue, except for this specific frequency, which doesn't get broadcasted anyway and wouldn't have enough energy to actually hurt you. So check out this video. So microwaves have a frequency of 2,450 megahertz. Calculate their wavelengths. So microwaves are part of the electromagnetic spectrum, so we can use C equals lambda F, and we want to calculate their wavelength. So we would just go speed of light divided by 2,450. So this is mega, so you'd have to look up what mega is, and mega is times 10 to the 6. So we'd have to plug it in like that. And we type these into our calculator. 3 times 10 to the 8 divided by 2,450 times 10 to the 6. And you get that microwaves are about 0.12 meters, or about 12 centimeters. Okay. So infrared, I'm going to show you these two videos here. This is old school Predator, and Predator, who was hunting Arnold Schwarzenegger. I want you to pay key attention to Arnold Schwarzenegger biceps. They're very impressive. So he was hunting Arnold Schwarzenegger, and he was able to see in infrared. So here's a video of them first spotting the Predator, and then the second video here is when Arnold Schwarzenegger finds out a way to beat Predator by covering himself in mud, which isn't super ridiculous because infrared doesn't have a great penetrating ability, so it'd be hard to penetrate through the mud, and when he cools himself down, it would work okay. So infrared wavelengths are a little bit bigger than visible light, and they aren't detected by the human eye, but Predator could obviously see it. And that Predator image are called false color images, and that's what light is seen through an infrared camera. So they just, infrared is heat a lot, so they just assign different colors to different temperatures. nerves on our body are sensitive to these frequencies, and that's why we can feel heat. So a use of infrared is remote controls for televisions. They're an infrared frequency, right? And if you're under the covers and you try to use the remote, it doesn't work because it can be blocked by the blanket, right? Another use I was talking about before of infrared is night vision cameras. So doorbell cameras, they shoot out infrared, which we can't see, but the camera can detect it, so it can illuminate objects in the infrared spectrum. So it's very advantageous for humans to be sensitive to these frequencies because infrared is heat and it can burn us and it can be a hazard. So that's good that our nerves can sense it. Yeah. So our next wavelength is visible light, and this is what we can see. So we can only see a tiny sliver of the electromagnetic spectrum that's from 400 nanometers to 700 nanometers. Red is the biggest wavelength, lowest frequency, and lowest energy. So this is why if you've ever been in a dark room where they develop photography, they always use red light because red is the lowest energy, right? This is the lowest energy, and then it gets higher in the violet. So that red light isn't enough to develop the film. Albert Einstein was the first person to classify light as photons, which has particles of their own frequency. So sometimes in questions they'll say photons, and that's usually for these higher energy light particles that we're talking about. So our next step up, higher energy, higher frequency, is ultraviolet light, and this ultraviolet light can be broken into 3 different categories. So here's a little chart of that. So right past, this is visible light that we can see, so just a little bit past visible light, we get UVA. And as we move this way, we get higher energy. So this is the lowest energy of the UV, and it can cause some wrinkling of the skin, maybe a possible link to skin cancer, but if you're exposed to a bunch of UVA, you would be okay. And then as we get higher energy, we get into UVB, which can cause a sunburn, proven link to skin cancer, cataracts in your eyes. So this is not good to be around. And then even higher energy UV would be UVC. It's ionizing radiation, which we'll talk about in a sec, and it can cause permanent damage to your DNA. And you'll see ozone layer is here, and this is because the ozone layer protects against these high energy UV photons, right? So if there's an ozone layer in the way, it blocks out these guys, and we don't get exposed to this damaging UV radiation. So here's a video. Again, we can't see UV light, but here is a camera sensitive to visible light, and here's a camera sensitive to UV light. So the cool thing about sunscreen is able to let all visible light through. So she's going to put the sunscreen on her face, and you see that things are the same because UV light can go straight through sunscreen. Or sorry, visible light can go straight through sunscreen. But this is a UV camera, and the UV light can't go through the sunscreen, so it's completely blocked out. So you'll see what happens to her face as she's doing it. So ionizing radiation. So anything past UV, so that UVC is the start of our ionizing radiation, and ionizing radiation is high energy radiation capable of ionizing material through which it passes. So this UVC photon can go penetrate through our skin, and it can reach our DNA. And when it goes and it reaches our DNA, it can break through those nucleotides, and it can break those chemical bonds. And when it breaks those chemical bonds, what can happen is there can be error in your genetic code when it goes back together, and it causes those mutations, which is really bad. And most of the time, mutations can cause cancer. So that is why ionizing radiation is so dangerous. So our next highest energy is X-rays, which I'm sure we've all heard of. And X-rays are produced by smashing fast-moving electrons into metal plates. X-rays are capable of penetrating tissue. But what happens is the more dense the tissue, the more the X-rays are absorbed. So bones are very, very dense, so it absorbs all the X-rays, but skin is not very dense, so the X-rays pass right through, and that's why it gives us this image. So skin and fat appear black because it doesn't absorb any, and teeth and bones absorb a lot, so they are white. So X-rays are dangerous. It is ionizing radiation. Doctors don't like to use X-rays unless they have to, unless it's going to cause more problems. Like a broken bone would cause a lot of lifelong problems if you didn't get a fix. So X-ray radiation is ionizing. It can damage your DNA, but the benefits of seeing inside your body, doctors need to balance the benefits of seeing inside your body with the negative effects of the X-rays. So what doctors use is the term ALARA, which is as low as reasonably achievable, and doctors will try to limit your exposure to radiation as much as possible. So when you get X-rays, they'll try to do a specific area of your body, or you'll wear those lead vests to sort of prevent anything else from happening or the X-rays getting anywhere else. And they use really low dose radiation X-rays. When you get your dental X-rays, it's such low radiation that you don't even need to wear one of those lead shields, but the time it takes to explain that to people is a lot longer than just giving them the lead shield that you wear, and it makes people feel safer. But you could have 100 dental X-rays in a year and you'd be 100% fine because it's super low radiation. The most dangerous cells for radiation are rapidly dividing cells like a fetus. So if you're a girl and you've ever been to a hospital and you had to get an X-ray, they ask you 4 million times if you're pregnant, because if you get an X-ray while you're pregnant, it would definitely damage the fetus and most likely kill it. So rapidly dividing cells are very susceptible to radiation. But the other type of rapidly dividing cells in your body include cancer. So if you had cancer, what you can do is you can shoot it with X-rays and you can kill the cancer. And this is called radiation therapy. So this is when a beam of X-rays is shot at cancer and is able to kill the cancer. So here's a video that just talks about the evolution of X-rays and where they go from here. So it also talks about MRI as well, which doesn't use radiation.
Exploring land, sea, and sky has taught us much about our world, and exploring the unknown frontiers inside our own bodies has taught us a lot about ourselves. The development of X-ray technology is one breakthrough in medical science that really got under our skin. At the time of its discovery, the X-ray astounded doctors and patients alike. It appeared to do the impossible: see through solid matter. What was so incredible then is now commonplace. For instance, the security industry uses X-ray screening to detect weapons hidden in luggage. Scientists use X-ray screening for a variety of purposes. Archaeologists rely on X-rays to determine the composition of ancient artifacts. Doctors examine X-rays to diagnose broken bones and illnesses. A few microseconds exposure to X-rays can generate still images of bones and teeth, as well as split-second still pictures of the heart in action. X-ray imaging has come a long way since it was invented in 1895. Before the invention of the X-ray machine, doctors had to make a diagnosis based on what they could see from outside the body. Since what they could see was so limited, doctors sometimes chose to do exploratory surgery just to make a diagnosis. In 1895, German physicist Wilhelm Conrad Röntgen discovered invisible radiation. He called his revolutionary discovery X-rays. Röntgen soon learned that radiation penetrated his hand, and within 6 weeks, he had figured out how to produce X-ray photographs. Röntgen took this X-ray image of his own hand. Röntgen also X-rayed his wife's hand. Her bones and wedding ring are visible because they absorb more radiation than her skin and muscles. His discovery generated immediate excitement. Doctors across Europe and the United States set up their own X-ray equipment. Working with X-ray equipment was dangerous for the patient and physician because they both received doses of radiation that harm internal tissues and organs. But physicians did not know this at first. The exposed cables on the early machines caused electric shock. Enclosing the tubes and wires greatly reduced the safety risks. However, the health effects of radiation remained a small risk for patients receiving X-rays. Computer-aided tomography is an imaging technique known as the CT scan or CAT scan. It is more powerful and sensitive than X-rays. CT scans produce clear, detailed cross-section images of organs and body structures.
Just have a seat on the table.
As valuable as X-rays are in medicine, another tool is even more effective, and it doesn't pose any known health hazards. Magnetic resonance imaging, or MRI, was first adapted for medical use in the 1970s. During an MRI scan, a patient lies on a table inside a large magnetic tube. The magnetic field inside the tube causes hydrogen atoms in the body to align. That is, the protons and all the hydrogen atoms face the same direction. When the machine beams radio waves, the hydrogen atoms enter a high-energy state. When the radio signals stop, the atoms return to the lower energy state, releasing energy in the process. A computer detects the released energy as tiny radio signals, which it uses to produce an image of the inside of the body. Magnetic resonance images provide much more detailed information than X-rays or computer-aided tomography scans. But MRI scans are usually more costly, so they're used less frequently. Doctors and researchers continue to find more ways to peer inside the human body using MRI technology. Scientists can examine the workings of the human brain by using MRI technology to make images of changes that occur as the mind thinks, talks, listens, dreams, and imagines. Better computer technology means MRIs can provide three-dimensional images of organs inside the body. Though the human eye cannot see through clothing or skin, X-ray and MRI machines give doctors a way to see inside the human body. This powerful technology presents endless possibilities for healthcare and other areas of exploration.
Okay, and then our last type of radiation that we're going to talk about is gamma radiation. So this is super high energy, high frequency, small wavelength, and it's only found emitted from radioactive material. So that's where we get gamma radiation from, is from radioactive things. So they have the highest frequency, highest energy, smallest wavelength. They are excellent at penetrating matter, and they come from the nuclei, which is plural of nucleus. They come from the nuclei of the atoms. Okay, and the last thing that you need to know is atmospheric interaction. So the sun gives off everything from radio waves to gamma radiation and everything in between. So it would be bad if we were exposed to gamma, X-ray, and ultraviolet from the sun, but luckily we have an atmosphere around us, and the atmosphere absorbs and reflects different wavelengths at different rates. So this chart shows what is blocked by the atmosphere best. So at 100% block rate, we have gamma and X-ray. And that is wonderful, because if the atmosphere didn't block that, we would all get cancer from these very, very quickly. And that's why when you're in an airplane, you get high doses of radiation because you don't have as much atmosphere in the way. So you get bombarded with these X-rays. And every time you fly on a plane, it's the equivalent of getting one X-ray. And then here, you can see this is the ultraviolet range, and it starts to dip down at the ultraviolet range, so it blocks some of those more dangerous ones like UVC, but UVA it doesn't block, and then it dips down to almost zero for visible light, so it lets visible light through, and then infrared it lets through at different rates. And this is still infrared, and then we have microwaves. It doesn't block any of the microwaves, and that's why we use microwaves for cell phone signals, because it's not blocked by the atmosphere, and we can send it to satellites up in space. And then super, super long are blocked out as well. But what you need to know, and what's most important to humankind for surviving, is X-ray and gammas are completely blocked by the atmosphere. So that's really important for you to know. Okay, I will attach a assignment with this, and that assignment isn't any numbers, so I will go through that with you tomorrow. Okay, so send me an email if you have any questions.